Ordering and causality. There are several reasons why ordering keeps coming up, and one of the reasons is that it helps preserve causality. We have already seen several examples over the course of this book where causality has been important. In consistent prefix reads on page 165, figure 5-5, we saw an example where the observer of a conversation saw first the answer to a question, and then the question being answered. This is confusing because it violates our intuition of cause and effect. If a question is answered, then clearly the question had to be there first, because the person giving the answer must have seen the question, assuming they are not psychic and cannot see into the future. We say that there is a causal dependency between the question and the answer. A similar pattern appeared in figure 5-9, where we looked at the replication between three leaders and noticed that some writes could overtake others due to network delays. From the perspective of one of the replicas, it would look as though there was an update to a row that did not exist. Causality here means that a row must first be created before it can be updated. In detecting concurrent writes on page 184, we observe that if you have two operations A and B, there are three possibilities. Either A happened before B, or B happened before A, or A and B are concurrent. This happened before relationship is another expression of causality. If A happened before B, that means B might have known about A, or built upon A, or depended on A. If A and B are concurrent, there is no causal link between them. In other words, we are sure that neither knew about the other. In the context of snapshot isolation, for transaction snapshot isolation and repeatable read on page 237, we said that a transaction reads from a consistent snapshot. But what does consistent mean in this context? It means consistent with causality. If the snapshot contains an answer, it must also contain the question being answered. Observing the entire database at a single point in time makes it consistent with causality. The effects of all operations that happened causally before that point in time are visible, but no operations that happened causally afterward can be seen. Read skew non-repeatable reads, as illustrated in figure 7-6, means reading data in a state that violates causality. Our examples of write skew between transactions, see write skew and phantoms on page 246, also demonstrated causal dependencies. In figure 7-8, Alice was allowed to go off call because the transaction thought that Bob was still on call, and vice versa. In this case, the action of going off call is causally dependent on the observation of who is currently on call. Serializable snapshot isolation, see serializable snapshot isolation SSI on page 261, detects write skew by tracking the causal dependencies between transactions. In the example of Alice and Bob watching football, figure 9-1, the fact that Bob got a stale result from the server after hearing Alice exclaim the result is a causality violation. Alice's exclamation is causally dependent on the announcement of the score, so Bob should also be able to see the score after hearing Alice. The same pattern appeared again in cross-channel timing dependencies on page 331 in the guise of an image resizing service. Causality imposes an ordering on events. Cause comes before effect. A message is sent before that message is received. The question comes before the answer. And, like in real life, one thing leads to another. One node reads some data and then writes something as a result. Another node reads the thing that was written and writes something else in turn, and so on. These chains of causally dependent operations define the causal order in the system, i.e. what happened before what. If a system obeys the ordering imposed by causality, we say that it is causally consistent. For example, snapshot isolation provides causal consistency. When you read from the database, and you see some piece of data, then you must also be able to see any data that causally precedes it, assuming it has not been deleted in the meantime. A total order allows any two elements to be compared. So if you have two elements, you can always say which one is greater and which one is smaller. For example, natural numbers are totally ordered. If I give you any two numbers, say 5 and 13, you can tell me that 13 is greater than 5. However, mathematical sets are not totally ordered. Is A, B greater than B, C? Well, you can't really compare them, because neither is a subset of the other. We say they are incomparable, and therefore mathematical sets are partially ordered. In some cases one set is greater than another if one set contains all the elements of another, but in other cases they are incomparable. The difference between a total order and a partial order is reflected in different database consistency models. Linearizability in a linearizable system. We have a total order of operations if the system behaves as if there is only a single copy of the data, and every operation is atomic. This means that for any two operations we can always say which one happened first. This total ordering is illustrated as a timeline in Figure 9-4. Causality: we said that two operations are concurrent if neither happened before the other. See the happens before relationship and concurrency on page 186. Put another way, two events are ordered if they are causally related. One happened before the other, but they are incomparable if they are concurrent. This means that causality defines a partial order, not a total order. Some operations are ordered with respect to each other, but some are incomparable. Therefore, according to this definition, there are no concurrent operations in a linearizable data store. There must be a single timeline along which all operations are totally ordered. There might be several requests waiting to be handled, but the data store ensures that every request is handled atomically at a single point in time, acting on a single copy of the data along a single timeline without any concurrency. Concurrency would mean that the timeline branches and merges again, and in this case, operations on different branches are incomparable, i.e. concurrent. We saw this phenomenon in Chapter 5. For example, Figure 5-14 is not a straight line total order, but rather a jumble of different operations going on concurrently. The arrows in the diagram indicate causal dependencies, the partial ordering of operations. If you are familiar with distributed version control systems such as Git, their version histories are very much like the graph of causal dependencies. Often one commit happens after another, in a straight line, but sometimes you get branches when several people concurrently work on a project, and merges are created when those concurrently created commits are combined. Linearizability is stronger than causal consistency, so what is the relationship between the causal order and linearizability? The answer is that linearizability implies causality. Any system that is linearizable will preserve causality correctly. In particular, if there are multiple communication channels in a system such as the message queue and the file storage service in Figure 9-5, linearizability ensures that causality is automatically preserved without the system having to do anything special, such as passing around timestamps between different components. The fact that linearizability ensures causality is what makes linearizable systems simple to understand and appealing. However, as discussed in the cost of linearizability on page 335, making a system linearizable can harm its performance and availability, especially if the system has significant network delays, for example, if it's geographically distributed. For this reason, some distributed data systems have abandoned linearizability, which allows them to achieve better performance but can make them difficult to work with. The good news is that a middle ground is possible. Linearizability is not the only way of preserving causality. There are other ways too. A system can be causally consistent without incurring the performance hit of making it linearizable. In particular, the CAP theorem does not apply. In fact, causal consistency is the strongest possible consistency model that does not slow down due to network delays and remains available in the face of network failures. In many cases, systems that appear to require linearizability in fact only really require causal consistency, which can be implemented more efficiently. Based on this observation, researchers are exploring new kinds of databases that preserve causality with performance and availability characteristics that are similar to those of eventually consistent systems. As this research is quite recent, not much of it has yet made its way into production systems, and there are still challenges to be overcome. However, it is a promising direction for future systems. We won't go into all the nitty-gritty details of how non-linearizable systems can maintain causal consistency here, but just briefly explore some of the key ideas. In order to maintain causality, you need to know which operation happened before which other operation. This is a partial order. Concurrent operations may be processed in any order, but if one operation happened before another, then they must be processed in that order on every replica. Thus, when a replica processes an operation, it must ensure that all causally preceding operations, all operations that happened before, have already been processed. If some preceding operation is missing, the later operation must wait until the preceding operation has been processed. In order to determine causal dependencies, we need some way of describing the knowledge of a node in the system. If a node had already seen the value x when it issued the write y, then x and y may be causally related. The analysis uses the kinds of questions you would expect in a criminal investigation of fraud charges. Did the CEO know about x at the time when they made decision y? The techniques for determining which operation happened before which other operation are similar to what we discussed in detecting concurrent writes on page 184. That section discussed causality in a leaderless data store, where we need to detect concurrent writes to the same key in order to prevent lost updates. Causal consistency goes further. It needs to track causal dependencies across the entire database, not just for a single key. Version vectors can be generalized to do this. In order to determine the causal ordering, the database needs to know which version of the data was read by the application. This is why, in Figure 5-13, the version number from the prior operation is passed back to the database on a write. A similar idea appears in the conflict detection of SSI, as discussed in Serializable Snapshot Isolation SSI on page 261. When a transaction wants to commit, the database checks whether the version of the data that it read is still up to date. To this end, the database keeps track of which data has been read by which transaction.